Hi, my name is Vittorio Di Cocco from Cassino University, Italy, and in this work I present a model able to predict the cycling behavior of a nickel titanium shape memory alloy characterized by a pseudoelastic effect, both in terms of microstructure evolution and stress-strain behavior. Considering that the shape memory alloys are characterized by microstructure changes due to the external loading, the question is which are the kinds of microstructures which can see in this kind of alloys, and which is the microstructure evolution. And another question is which is the influence of the microstructures when on the behavior of material in terms of stress strain. In this work, we propose a simple model able to describe the mechanical behavior of the shape memory alloy characterized by a pseudoelastic effect, which take into account the microstructure, the real microstructure of the material. In order to better describe the phenomena, we start from the experimental results. And the first step has been to produce the material using a vacuum crucible posed in a furnace without air and using a noble gas like argon in order to eliminate oxygen inside. We use the crucible made on yttria because the yttria is very stable in terms of chemical action, and the casting have been in a mold made on graphite, as you can see in the slide. The product of the casting is the ingot. It's a very short ingot. The height is around 5 centimeters, and the material has been characterized both in terms of the chemical composition. You can see that the quantity of the nickel titanium in atoms is quite similar, and in terms of microstructure you can see the magnification. This is around 500 per of magnification. Then starting from the ingot, mini dog bone specimen have been produced like this. You can see that the calibrated length is around 16 millimeters, and the total length of the specimen is 13 millimeters. This specimen has been put in a tool. It's a mini machine, patented mini machine, which allow us to perform a loading test using load cell in order to measure the total force applied on the specimen, and with an LVDT we can control the movement of the crosshead. This tool is able to put under load the specimen inside of machine able to perform the XRD test in order to observe the diffraction spectrum, which is the base to better understand the position and of atoms, and in this case the structure, the microstructure. Tests have been performed by using a loading unloading cycle test, and here we can see the first cycle split in two different cases. The first one is the loading condition, with the presence of the first stage characterized by the presence of austenite. The second stage is the plateau, but you can see the plateau is not characterized by a slope equal to 0, but the slope is greater than 0. It's the minimum slope that you can see in these curves. Then over we have the third stage characterized by the slope of the martensite. In a loading condition, you can see the third stage is wider than the first one in loading condition, and then we have a different second stage where we have a transformation of martensite in austenite. Is a reverse transformation, and then the first stage is very short here, characterized by the recovery of elastic energy of the austenite. In order to analyze the position of atoms at the microstructure, we have to perform the diffraction, X-ray diffraction on the specimen, and we use the tools described in the previous slides, using a step-by-step technique. The step investigated in the loading condition, starting to the unloading condition. Then we have used the different steps, 2.5% of engineering deformation and so on, up to 10% of engineering deformation. And then in back direction, we used a loading steps in order to perform the diffraction on the calibrated length under load. In this slide, I show the spectrum of the unloaded specimen. We can see that we have a presence of a first peak here, and the presence of a second peak in this position, and the third in this one. Analyzing this spectrum, we can see that this structure is the structure of a cubic lattice, characterized by the position of nickel atoms on the vertex of the cubes, and the titanium atoms are inside of the cubes. Considering the spectrum obtained at high values of deformation of the specimen, with an engineering strain of 10%, we can see that the first peaks disappears, and we have the presence of another peak in this position, and another one here and here. Analyzing the structure, we discover that the new structure is a monoclinic structure like this, and here we propose the position of nickel and titanium atoms on the vertex of the structure. In order to modelize the variation of a microstructure, we hypothesized the presence of energetic potential E, which depends on deformation epsilon, but depends on the quantity of austenite and martensite too. In differential form, the variation of this potential it's equal to the linear contribution of the deformation epsilon, which multiplied a constant c. In this case, the model is perfectly linear. It's the model that we can see in literature. But in this case, we use the contribution 2 of the austenite in this manner, the variation of austenite on the quantity of the austenite, plus the contribution of the martensite at the same manner, but using a negative sign, because we postulated that the austenite transforms in martensite and vice versa without any other phases, intermediate phase. The equilibrium takes place when this differential is equal to 0, like this. And integrating this equation, you can see that the formulation is very, very easy. A constant D is equal to the constant C, which multiplied the deformation plus the logarithm of austenite on the martensite. Taking into account that the summation of quantity of austenite and martensite is equal to 1, you can calculate the quantity of martensite like this and the quantity of austenite like this. This and this are the equations which calculate the quantity of martensite and austenite during a deformation process characterized by an epsilon of deformation level. Considering the results in terms of quantity of martensite and austenite taken from the step-by-step tests in loading and unloading condition at the first cycle, we can calculate the values of the parameter C and D. You can see that the C is always equal to 1 and D changes from 700 to 70 and in this case the parameter D takes into account the hysteresis of the material. In the graph you can see how the plotted functions seems fit well the quantity of measured microstructures. Calculating the parameters not only for the first cycle but for the 10th cycle, you can see that the parameter C changes from 1 to 0.9 and the parameter D are always the same in the loading and unloading conditions. Next, at the 50th cycle, the parameter C decreases again, and after 100 cycles decrease too. Plotting the parameter C in terms of the cycles, you can see a behavior like this. It means that the parameter C takes into account a sort of a fatigue effect in the shape memory alloys. In terms of mechanical behavior, we can calculate the real Young modulus of material as an easy weighted summation of the Young modulus of austenite and the martensite. It's a very easy formulation, but it doesn't work. It doesn't work because the slope, in this case, starts from the slope of austenite, arrive to the slope of martensite, and no decrease of slope can describe. Why it doesn't work? It doesn't work because not all the structure are involved in mechanical process. For example, during the tensile test in loading condition, the quantity of austenite which is transforming in martensite, the contribution is in terms of increasing of stress is very low. So we have to correct this quantity of austenite, take into account the quantity of the austenite which is changing in martensite. How? In this way, you can divide the quantity of austenite to 1 plus coefficient K of austenite multiplied the variation of the quantity of austenite in deformation epsilon. In the same way, we can correct the quantity of the martensite, which are multiplying the elastic modulus of martensite. The equation of austenite and martensite are calculated by previous model, and the variation formulation are very easy to write. As we can see in the pictures, these parameters decrease in the cycles in all investigated conditions. In particular, in unloading conditions, the Ka seems to be not so influenced by the cycles. Anyway, the Ka parameters weakly decreases, and in loading condition sharply decreases. Km parameter seems to be strongly influenced by the cycles both in loading and in unloading conditions. You can see that the values of the Km parameter in loading condition ranging, for example, from 200 down to 55. But in all cases, we can see that these parameters decrease in cycles in all investigated conditions. This is the formula proposed in this work, and here you can see the stress-strain behavior at the first cycle. We can see that the calculated values seems to fit well the experimental results. In the same way, we can see the comparison between the model and experimental values at cycle 10, then at cycle 50, and finally at cycle 100. In conclusions, in this work we investigated the cycling behavior of a shaped memory alloy characterized by a pseudoelastic effect, both in terms of microstructure and in stress-strain behavior at 1, 10, 50 and 100 cycles. From the experimental results, we can see that the austenite-martensite transformation in loading conditions and the inverse martensite-austenite transformation in loading conditions are not linear. Then, the stress-strain behavior is influenced not only by the real quantity of austenite and martensite, but also by the quantity of austenite and martensite which are transforming, because the transforming phase doesn't participate to the increase or decrease of stresses, but use the energy for the microstructural transformations. Finally, we proposed a simple model which, starting from the real structure of the alloy, is able to predict the cyclic stress-strain behavior of a shaped memory alloy with a pseudoelastic effect. Thanks for the attention.